All right. Okay. So here I think we'll start. Last time we were doing this problem, we did not get the time to complete it. So we'll start from this problem and then we'll proceed further. Right. Before I get to that, anyway, is there any question from the topics that we were talking about before? We discussed potential energy, kinetic energies, and the total energy of an oscillator. We also the velocity and displacement relation. Anyone? Alicia or Anna? I cannot hear you for some reason.
Yes.
Yeah. Okay. So, all right. So you got this relation? V
Yes.
versus displacement. Right. Okay. Okay, good. So this is the relation that we derived. We use this velocity to write down the kinetic energy of any oscillatory motion. We saw that the maximum kinetic energy of such type of motion depends on the extreme position of the oscillation, which is x naught. That is also the amplitude of the oscillation. And from there, we used the definition for the elastic potential energy to write down the potential energy of any simple harmonic oscillator, and which was this. And then we found that the total energy, which is the sum of the kinetic and potential energy of the system, just turns out to be the equal to the maximum kinetic energy or the maximum potential energy. Can you take a guess why this thing, why the total energy of such an oscillator is always equal to a maximum? Because if you see the maximum potential energy from this expression is also half m omega squared. And when would be the potential energy maximum? When it would be when the oscillator or the pendulum would be at its maximum displacement from the mean position, right? That's when it would have stored maximum amount of potential energy. So that position is x naught. So I'll replace this x squared with x naught squared. So you see that this thing is also equal to, this is the maximum potential energy, which is equal to the maximum kinetic energy, right? Which is equal to the total energy of the oscillator. How is that possible? Can anyone take a guess? Why is that so? It's not surprising at all. It should have been like this. We should be expecting this result. Can anyone tell me why? I'll give you a hint. Think about the conservation law of energy.
What was the question again?
The question is that we see that the maximum potential energy would be half m omega squared, and in place of this x squared, I'll put x naught squared, right? Because the oscillator would have its potential energy maximum when it's at a maximum height that it can possibly be, right? Or maximum displacement that it can have. That's potential energy, right? So, and we also derived that the maximum kinetic energy is also equal to half m omega squared x naught squared. And then when I wrote down this total energy by adding those two, we saw that the total energy of the system is also half m omega squared x naught squared. How can the total energy of a system be exactly equal to the maximum kinetic energy or the maximum potential energy of such a system? The key word here, I'll give you hints. The key word is maximum, and the second is hint is that think in terms of conservation of energy. Can you
Yes.
Give me.
And that's because when the potential energy is at its maximum, the kinetic energy is zero. And when the kinetic energy is at its maximum, the potential energy is. So at the end of the day, we have the same total energy.
Exactly, right. So yeah, exactly. So that's the answer that I was looking for. Uh, all right. So who gave me that answer? Was it Alicia or Anna?
Alicia.
Alicia. Right. So Anna, do you understand this as well?
Yes, sir.
All right. Okay. Perfect. So that's the reason. Because and the reason for this is again the conservation of energy. To conserve energy, this has to be true. All right. Okay. So that's what we covered so far, and we were doing a problem. I'll just quickly restate the problem. The problem was that you have a pendulum, and the time period of such a pendulum is 2 seconds, where the mass of this pendulum, the bob that is attached to the string, is 200 grams, right? Uh, so actually, let's make it 600, and then suppose that I raise this pendulum to any height and then release it. The height that I raise it to, or the displacement actually that I give it, would be the amplitude of the oscillation, and that's 5.2 centimeters. So that's the value of x naught. Now, you want to find out the kinetic or the maximum kinetic energy of this pendulum, meaning you will have to find out the maximum speed of this pendulum, right? So to find out the maximum speed of the pendulum, where would the speed be maximum? That's the first thing that you have to know. In this entire course of its oscillatory motion, at what point in this motion would the speed be maximum? Anyone?
The speed is maximum when it's in the middle.
At the middle point, right? At the center, because at this point, it will be having the maximum velocity, because at this point the gravitational potential energy is minimum, means that the kinetic energy is maximum. Hence, the velocity at this point should be the highest, right? So then if I use this expression for the kinetic energy, which is what? Half. Let's at this point, I'm not talking about maximum kinetic energy or anything. We're talking generally about the kinetic energy of the oscillator. That would be half m omega squared x naught squared minus x squared, right? So now we want the point that is at this middle, that is at the center or the mean position. So x would be 0 at mean position, right? And then we go back to the expression for the maximum kinetic energy, which is this one that we wrote over here. Now, I was telling you last time that if you remember from a circular motion, we talked about how can I relate the tangential velocity component with the angular velocity of a motion, right? And that relation was with this thing, v is equal to r times omega. R was simply, if we're talking about a circular motion, then r is the radius of that oscillation, of that object that is oscillating in a circle. Of course, in any general case, x, it would be x naught, or just any x, right? Not any x, it should be the amplitude, the maximum displacement, right? If you remember the example for a circle, it was something like this. I have this radius. So this is the maximum distance that this bob is away from the center of the circle and moving in this direction, right? So then we have this relation. This relates v, the tangential velocity, with the angular velocity. And of course, in kinetic energy, we have half mv squared, right? So if I want to calculate the maximum velocity, then I need this maximum velocity, right? So I can well, I can reduce or write this expression kinetic energy as half mv squared, right? And this v is the tangential velocity of the oscillation. So to find out this velocity, all I need to do is rearrange this expression as 2 times the kinetic energy. Now we want the maximum velocity, so we should have the maximum kinetic energy. And what is the rest? We'll divide this by the mass, right? And then square root this thing. So I just rearranged this expression into this one. Now we are given the time period. The time period of the oscillation is 2 seconds, right? So then finding out this value for omega is very simple. You just have to remember that omega was 2 pi divided by t, or just 2 pi f, right? But f is 1 by t. F is the frequency of the oscillation. So just put in the values and you would get omega as 2 pi by 2 is just pi radians. So any question at so far?
No, sir.
All right.
No.
So, okay. So now we can easily find the maximum kinetic energy, right? So the maximum kinetic energy, which was half m omega squared x naught squared. I have omega now. I have x naught, the amplitude of the oscillation. We have the mass. So just put in these values. Mass was 600 grams, so that would be 0.6 kilograms. Omega is pi radians. We'll square this thing and then multiply this with the amplitude of the oscillation, which was 5.2 centimeters, right? If you it was given in the problem. So just write it as 5.2 into 10 raised to power minus 2 meters, right? And now all you have to do is just do the math, right? And this would give you the maximum kinetic energy as 8 point something, 8.0 into 10 raised to power minus 3 joules, right? So now the first part of the question is completed, which was to find the maximum kinetic energy. And now it's very simple to find the maximum velocity, because the maximum velocity is, or we derived this relation before this one, right? So this relation, the reason that I was deriving this was to compute the second part. And so the maximum velocity is just square root of 2 times this kinetic energy, which is this thing, divided by the mass, which was 600 grams, so 0.6 kilograms. And then you just do the math, and this gives you 0.16 meters per second. So is it clear? This is the velocity. This is the maximum velocity with which the pendulum would oscillate at its mean position. So if I release this pendulum, it's going to start oscillating like this, and then it's going to come back. When it comes back, it's crossing this mean position. At that point, its velocity would be a maximum of 0.16 meters per second. So is there any problem in this question? Is
No,
that okay?
sir.
No problems? All right. Okay. So if that's clear, then let's move on to the next topic. We have only 2 topics left: resonance, right? And then we'll talk about damping. So first, I guess let's talk about resonance. Now, all right. So you can is everybody familiar with the idea of we can use sound waves to break a glass, right? Sound can be used to break a glass. Is everyone familiar with the fact?
Yes.
Right, so it's because we have these you get enough energy from the sound waves that can overcome the energy required to separate the the you can say the atoms or the molecules that have made up the glass. And so why is that? How is that possible if you think in terms of these waves? uh, you know that it doesn't matter, but everything that you see, it's made up of atoms, right? Everything is made up of atoms, whether it's a glass, whether it's a plastic, or whatever it is, it's made up of atoms. Atoms are never sitting still. They're always vibrating. It doesn't matter if it's a solid, it's a liquid. It's crystal clear that in a gas, the atoms are not moving at all. I'm sure that by this time you're all familiar with the fact. But even in a solid, the atoms are not sitting still. They are moving, they're jiggling around in their structure. So because of that fact, if they're moving, they're essentially vibrating, and they have some frequency with which they oscillate, with which they're vibrating, right? And this frequency is called the natural frequency. I'll just call it omega n, right? Sometimes you call it omega naught, or you can give it any name, but this is known as the natural frequency of any object, right? Now, what does that tell you? That tells you that this is the maximum frequency that the object can bear to stay in the structure that it is in, right? If I give it any more frequency, if I somehow supply it enough more energy, right, then what would happen is that frequency would overcome this natural frequency, and then that would change the structure of the object. So by changing the structure, I mean, if it's a glass, it could break, right? And that's why the glass breaks, because what you're doing is you're giving it enough amount of vibrations with such a higher amplitude that the frequency that you're providing it becomes either equal or greater than the natural frequency of the oscillation. And so then the structure changes. This is the reason that some of the buildings may collapse. Bridges might also collapse if there is a heavy machinery over there, if there is, or even in the constructions of building, if there is a machinery that's so heavy, or it's vibrating, it's vibrating so heavily that its frequency it's greater than the natural frequency of the building, then the building would collapse, right? So is the idea of natural frequency clear? That it's a frequency that every system will have. Every system has a frequency, right? That is its own frequency, right? And this frequency is dependent on obviously on the material that the object is made up of, on the size of the object, on how heavy the object is, and how the atoms are arranged, right? In any specific material, how the atoms are arranged. Different arrangement of atoms correspond to different materials, right? And so this, in an engineering language, it's called the design of the material or the object, right? So it could be the design of the building. And so that's a frequency that every system is going to have. Any frequency that is greater or equal to this frequency is critical for the system. It can cause the collapse of the system entirely, right? So then the frequency that I provide the system is also called the driving frequency. So this is the frequency that I'm providing the system, which can be higher than the natural frequency. So for example, if a system is sitting still, right? Any object is sitting still. Suppose this is a block, and this block is going to have its own natural frequency with which the block is, the atoms the block is made up of, and those atoms are vibrating in their doing their own thing. And then all of a sudden I come and I push the block, kick the block, or whatever. What I'm doing to the block is I'm giving it some driving frequency, right? And that frequency, I'll just call it omega. If I give this that, when I kick it or push it or apply any sort of force to this object, then what I'm doing is I'm just giving it some more frequency. Now, if this frequency omega is greater than or equal to omega natural, which is the natural frequency, then resonance happens. Right? So driving frequency is nothing but the external frequency, right? That I might provide to the system apart from its own natural frequency. So that means if the external frequency is greater than the system's natural frequency, then you're going to cause all types of disasters, collapse of buildings, bridges. You may even so for example, if there is some machinery that's operating, and the machine operates, when a machine is operating, you're familiar with the fact that it's vibrating as well. And if the vibrations are so large compared to the natural frequency of the machine, then the machine might break as well, right? So these are some of the things that you have to keep in consideration when even designing systems. So this external frequency is related to types of oscillations that are called forced oscillations, right? Because obviously, if you think about this, this example that I gave, that you have a block and you kick the block, you're forcing some oscillations in the block. Initially, it was not oscillating. It was just sitting. It was oscillating with its natural frequency, but I forced some oscillations on it by kicking the block, and hence these type of oscillations are called forced oscillations. And then you can solve the differential equation that I wrote last time. If you remember, it was m d square x by dt squared is equal to, it was minus kx. If you remember this equation, right? We wrote this down when we started this topic, this chapter. And now the forced oscillation, there is some external force, right? So I'll just add that external force in this differential equation. Now this capital F is the force that I might have kicked the block with, and that those kind of forced external forces. Now if I solve this differential equation, I'll get a different solution. Remember last time we got x is equal to x naught sine omega t. Now the solution will not be the same. This would not be the solution. The solution would be different, and that solution would also account for this force F, right? So of course, now solving this differential equation is a bit more complicated. It's in fact sometimes also called an inhomogeneous differential equation, and so that's not the part of the course. So we'll leave this thing just to that. I'll just show you a graph between the frequency and the amplitude of the oscillations, right? For a resonance case. So if I have frequency over here, and suppose I have any amplitude x naught over here, any x, right? So the graph looks like a sharp peak, right? And the amplitude is maximum when the frequency is equal to the natural frequency, right? That's when the amplitude is maximum, and that's when all the disasters can happen, right? Collapse of buildings and so on that we talked about, right? So this type of a graph is known as a sharp peak curve. And for all the resonance, you will observe this the graphical representation as a sharp peak curve. So that's a resonance. Is that clear for everyone? Any questions from the topic of resonance?
No, sir.
All right, amazing. Okay, it just occurred to me all of a sudden, Alicia, I just remembered that yesterday you shared your email address for for me to share the recordings of the lectures, right? I forgot. Can you please remind me after the class again? So immediately I'll do this after the class, right? So just remind me after the class is over, just text in the group or so on. Do remind me. Okay, so after this thing, now we can talk about damping. I hope we have enough time. You have 7 minutes. All right. Okay, so now let's finish this chapter with the topic of damping. All right, so damping is something that is you'll always practically observe in your oscillation. So far, we have been talking about graphs that looked like this. Let me just draw. So our graphs followed this sine or cosine functions, and they looked something like this, right? So their peaks were always at the same height, right? So it's like this. They're always at the same height. Now, this type of oscillations are not practical. Practical as in you would not observe these type of oscillations on a daily basis. The type of oscillations that you will observe are they look something like this. So let me try to draw it. So you have this curve, then you have this, and then now it starts to decrease. Right? And something like this. So you can clearly see this thing that if I draw a line like this, you can see that these peaks are decreasing. They're going downwards. Why do you think that this should be a more realistic case compared to the first one? Can you think of any reason why should the second case be a more realistic case? Okay, so basically, when anything is oscillating, for example, I'll again start with the example of this pendulum. If this pendulum is oscillating, then what is happening? The pendulum is suspended in a room, right? And of course, in a room, there are going to be particles, air particles, right? For example, there could be air particles. That's the most simplest case. And this pendulum, this bob, is going to collide with these molecules of air, right? As it's oscillating, these air molecules are going to come into its path, and it's going to collide with these air molecules. And when it does that, what it's doing is it's transferring its energy into these molecules. And at the end, what's left is this bob with less and less and less amount of energy. Right? So it's losing its energy into the environment. And that loss of energy would mean that its amplitude of the oscillation would start decreasing, decreasing, and decreasing. And that's the reason that when you oscillate a pendulum in a simple room, then you will observe that the pendulum eventually comes to a stop at its mean position. Otherwise, if you were doing it in a vacuum, for example, in a perfect vacuum, the pendulum will go on forever. It will never stop because there is nothing that the pendulum can collide with and transfer its energy to. So the pendulum, the bob has to lose its energy to the environment to eventually come to a stop. And what that means for the amplitude of the oscillations is that that would decrease the amplitude of our vibrations. And so we can see that the amplitude here is higher compared to the amplitude here, and then that's higher compared to here, and then that's higher compared to here. But as we move further and further, the amplitude keeps on decreasing, and eventually it will decrease to 0. So is that clear?
Yes.
Is this up until this point damping is clear?
Yes, sir.
All right. So now to cause damping, you can cause damping by several means, right? You can cause damping by performing your oscillations in some type of a fluid. For example, maybe if I oscillate in water compared to air, the oscillations would damp very quickly in water because now it's easier for the bob to collide with molecules of water because the molecules of water are even more closely packed together, right? Compared to the molecules of air, which is just a gas and the molecules are roaming around here and there. But for a liquid, the molecules are even closely packed. So it would be easier to distribute the bob's energy into these molecules. If in turn I use, instead of water, I use oil, then it would be even more harder for the bob to oscillate for a long time. It would die out even quickly, right? Because in oil, the density is high. And it's high, meaning that there is more oil packed in the same amount of volume compared to water. So there are more number of molecules that are packed in the same amount of volume as water. So then it would be even harder, even easier to distribute the energy of the bob into these molecules. So this takes us to the types of damping. And there are three main types of damping, right? The first one is light damping. And for a light damping, the graph looks exactly like the one that I drew. Then there is something that is called critical damping. In critical damping, the vibrations are going to die out very quickly. So, for example, oil could be an example, right? And the graph would look something like, they would die out very quickly, right? At this point, now they're just dead, right? So they're zero. Now there is no more oscillation further from this point. Then there is the third one, which is called heavy damping. In heavy damping, the oscillations die out, right? They die out